Hello ib2 higher level students. Okay, welcome. Next recording, next video lesson related with your nuclear physics for higher level. Today we'll be talking about matter waves, about wave-particle duality, and about de Broglie hypothesis. Okay, at the end we'll solve a few exercises from SOCOS. Okay, so last lesson was about photoelectric effect. We wrote the test. And in photoelectric effect, light, so classically wave, okay, must be photoelectric effect cannot be explained by the wave nature of light. We cannot use light as a wave to explain photoelectric effect. So to explain it, we use term photon or particle of light. A quant of light, the energy of light, portion of energy of light. Okay, so today we'll be talking about opposite phenomenon. How, if light is a wave and a particle, then the classical particle like electron can be a wave or not. Okay, so write the topic matter waves. Okay, and point number 1, wave-particle duality. Okay, so let's start with first question. Is light a wave or is it a particle? Okay, is light a wave? Or is it a particle? Is it a particle? Okay, so what is the correct answer? Okay, light is of course a wave. Yeah, we have few phenomena or few experiments where light must be a wave, like diffraction of light. Okay, so light is a wave. So is it a particle? In the case of photoelectric effect, yes, we have a photon, which is a particle of light. So what is the correct answer? The correct answer in this question is light is a wave and light is a particle, depending on the experiment. Okay, we can describe diffraction only by using wave theory of light, and we can describe photoelectric effect only by using term photon, so particle theory of light. Okay, so let's state another question. Okay, if light waves can show particle properties, maybe let's write this. If light waves can show particle properties, okay, can particles such as electrons, yes, or protons, show wave properties? Okay, so we know that particle is a particle. Let's take electron. Okay, electron has a mass. We can localize electron. We can talk about speed of the electron. We can accelerate electron to high speeds, to low speeds. So electron is a matter. Okay, a piece of matter. Yeah, elementary particle, piece of matter. But the question is, can be a wave or not? Okay, so what is the correct answer? Again, correct answer is yes. Okay, if we are talking about electron, yes, then we think about little particle have defined size, shape, position, speed. Okay, but we have phenomenon called diffraction of electrons. More details later. And diffraction of electrons means that in order to diffract, electrons must have a wave nature. Okay, so right here term diffraction of electrons, and this phenomenon can be explained only by wave nature of particles, wave nature of electron. So electron or other particles show wave properties. Okay, and this is today's lesson. We will be talking about something which is known as de Broglie hypothesis or waves of matter. Copy this slide, okay? When you will be ready, turn the video again and it will be equation, yeah? Okay, point number 2, de Broglie hypothesis. Okay, scientists de Broglie first described mathematically the relation between world of waves and the world of matter. Okay, so he gave equation linking the wavelength of this wave of matter with another properties related with particles like mass and speed, or basically by momentum. Okay, so what is his equation? His equation is simple. He links wavelength of matter wave with momentum by simple relation where h is of course Planck constant. Okay, p is a momentum and lambda is of course the wavelength of matter wave. Okay, of course he called these waves of matter de Broglie waves, and the wavelengths of these waves as de Broglie wavelengths. So here we can also use term de Broglie wavelength. Okay, relation looks simple, okay, but you will see in exercises that it's true, okay. Okay, so what is here? Left hand of this equation is a wavelength. So typical property of the wave, the base property of the wave. Right hand of this equation includes momentum. So a typical property or quantity related with matter. Remember, momentum is a product of mass and velocity, is a vector, yes? So if we have a particle of given mass which travels with a given velocity, it has an associated wave of wavelength which is given by this equation. It doesn't mean that each object of given mass and speed is a wave. Yeah? It means that particles have a wave properties, and by using this equation we can in simple way we can explain diffraction of electrons. Okay, so what is diffraction of electrons? When electron travels through the slit, okay, then if in the other side of the slit we have a detector, yes, we can detect electrons in certain positions, obtaining something which looks like interference pattern. We have places where we have more electrons and places when we have less electrons, so typical diffraction, sorry, not interference, I said interference, typical diffraction pattern. So how is it possible to make a diffraction pattern by electrons? Okay, you can imagine you can say that maybe electrons bouncing one with another, creating such a pattern. But scientists created a very narrow stream of electrons. They, let's say, ejected electrons one by one. And after hours and hours, detector or detectors detected electrons at certain position, which means that electrons create a typical diffraction pattern. Okay, so maybe stop video for a moment and turn on another movie, not my movie. Write in YouTube Dr. Quantum diffraction of electrons. Probably I've presented this movie to you in middle school. Okay, so it's a few minutes long, I don't know, 6, maybe 7 minutes long. So please stop this video for a moment. Write Dr. Quantum Diffraction of Electrons. Is cartoon movie with guy who is similar to, I'm not going to use name, to Mr. Biology teacher. Yes, you will see. And watch this movie because it's nice to see this at this moment. When you will finish, please turn this video and I'm going to continue. Okay? Okay, so still we are talking about the Broglie hypothesis. Again, I'm going to write this equation. Okay, let's imagine, let's calculate maybe the wavelength of electron which is accelerated through a potential difference. Let's imagine that you have an electron which is accelerated by potential difference of 200 volts. What do we know about electron? We know its mass is 9.11 times 10 to the power of minus 31 of kilograms, and we know its charge 1.6 times 10 to the power of minus 19 of coulombs. Okay? And we know that the electron is accelerated by potential difference of 200 volts. And of course, Planck's constant is 6.63 times 10 to the power of minus 34 joule second. Okay? Now your task is try to find the Broglie wavelength of such electron. Is it clear? Stop video. You have, let's say, 7 minutes. Okay? Find the Broglie wavelength of this electron. After 7 minutes, turn it back and I give you a solution. Okay, 7 minutes later. First of all, you have to calculate energy gained by electron by multiplying its charge, 1.6 times 10 to the power of minus 19, times a voltage, 200 volts. So this is 3.2 times 10 to the power of minus 17 of joules. Okay. Second, you have to use equation linking momentum and energy. Okay, P momentum is the root of 2em, which is the square root of 2 times energy, 3.2 times 10 to the power of minus 17, times mass of electron, 9.11 times 10 to the power of minus 31, all in standard units. I have a powerful calculator, new Casio. I'm going to use it. Okay, so this is the square root of 2 times 3.2 times 10 to the power of minus 17 times 9.11 times 10 to the power of minus 31, and I have an answer 7.64 times 10 to the power of minus 24. This is momentum, so kilogram times meter per second. And finally, we can use equation, the Broglie equation. So Planck's constant 6.63 times 10 to the power of minus 34. This is 3, this is 4, or just minus 34 divided by momentum, which is 7.64 times 10 to the power of minus 24, which is calculator divided by bracket 7.64 times 10 to the power of minus 24, close the bracket, it is 8.67 times 10 to the power of minus 11 of meters. So let's look. So what is the result? You can imagine that you have an electromagnetic wave, like a light, but not visible, which has a wavelength of 8.67 times 10 to the power of minus 11 meters. And this electromagnetic wave will give us the diffraction pattern, which is the same as diffraction pattern of stream of electrons accelerated by potential difference of 200 volts passing through slit of the same size. Okay? Remember, diffraction takes place when gap or aperture for which light or electron travels is in the order of magnitude of wavelength. So what does it mean? It means that we can use the stream of electrons to measure, to study a matter, because let's look, 0.7 times 10 to the power of minus 11 is the order of magnitude close to 10 to the power of minus 10 of meters. This is typical size of the atom. So this is, you can imagine that stream of electrons travels through matter, and distance between atoms or atoms behave as obstacles on the way of electrons. So we can observe diffraction by using electrons traveling through matter. So basically we can study matter. If we know potential difference used to accelerate electrons, we can use typical diffraction formula to find a minimum angle of where the number of electrons is the least, and due to this we can calculate the spacing between atoms in the matter. So basically we can study matter. Is it clear? Okay, so point number 3, electrons diffraction experiment. Electron diffraction experiment. Okay, so how can we do this, what I've described? Okay, so let's imagine that you have a heater, a kind of filament, okay, which emits by phenomenon called thermal emission, which creates electrons, okay, and these electrons are accelerated by potential difference. In our example, it was 200 volts. It can be 1000 volts. Doesn't matter. So this is our accelerating potential difference. I'm going to write accelerating potential difference. Difference. Accelerating potential difference. So these electrons are accelerated through this potential difference. Okay, so are traveling faster, faster, and faster. And here we have a sample. Okay, originally it was powdered graphite. Okay, of course this is in vacuum, so we have something like a bulb. Oh, here. Okay, and what is observed on the screen here? We can observe diffraction pattern in the form of circles, so places where we have more electrons and places when we have less electrons, because stream of electrons is diffracted. Okay, by what? By spacing between graphite. Why circles, not lines? Because graphite is powdered, so we have a lot of orientations. So electrons will be diffracted in all directions, creating diffraction pattern in the form of circles, not lines. Okay? And let's write last point. Historically, it was done by two scientists, Davison and Germer, in 1927 in a little bit different way. So write point number 4, Davison and Germer experiment. And I remember it was in 1927. Okay, they measured diffraction of electrons a little bit differently. They used similar apparatus, a filament lamp, producing electrons by temperature. Okay, you know that electrons can be emitted from surface of metal by photoelectric effect or by high temperature. Temperature can also remove electrons from the surface of metal, so this is why filament is a good producer of electrons. Okay, these electrons must be accelerated. So here between these lines we have accelerating potential difference. Okay, and electrons were directed to the target we want to measure. Okay, and due to the diffraction, electrons, okay, make a kind of angle. Let's name this phi. Okay, and this angle can be measured by using a movable detector. Okay, and at one angle we can observe less electrons, and this angle is typical the angle of minimum of diffraction pattern. So we can imagine that you have something like this. A lot of electrons, and for a given angle we have less electrons. So this is intensity of electrons versus angle. So for one given angle called minimum, we have less electrons. So it you see it's very similar to typical diffraction pattern when angle of minimum is lambda over b, the spacing. Is that clear? Okay, so let's back to mathematics. Open your Tsokos. I hope you have Tsokos, and I hope I also have Tsokos. Yeah. Open your Tsokos on page number 503. 2 to the power of 9 minus 3 to the power of 2. Okay, and here we have few exercises. Exercise number 13, 14. I'm going to copy it. And exercise number 15. Okay, I'm going to do one exercise with you. The rest will be your homework. Of course, don't waste your time. Do this now. Still, you have a lot of time to the end of the lesson. Okay, in exercise number 13, we have a brick which is moving. Estimate its de Broglie wavelength and comment whether it makes sense to treat the brick as a wave. So it's easy. You can do this working alone. Exercise number 14, describe experiment in which then the Broglie wavelength of an electron can be measured directly. So we've described on previous page. And B, determine the speed of an electron whose de Broglie wavelength is equal to that of red light. So it's also not challenging because you have wavelength. By using the Broglie hypothesis, you can calculate the momentum, and momentum is mass times speed, so you can calculate speed. So let's do together exercise number 15. So please stop video for a moment, do exercise number 15 in, let's say, 1, 2, 3, 4, 5, 6, 7, 8 minutes, 9 or 10 minutes. We will check together exercise number 15, and then you will do exercise number 13 and 14 working alone. Okay? So exercise number 15, when you will be ready, turn video back. 10 minutes later. Okay, exercise number 15. Show that the Broglie wavelength of an electron that has been accelerated from rest through potential difference is given by. Okay, so let's look. Wavelength is h over p. Okay? You know that E is p squared over 2m. So we can write h over the root of 2em, because this is p. And you know that energy of electron is its charge times potential difference. So finally we have Planck's constant divided by square root of 2 times mass times charge of electron times potential difference. So this is something you had to find. Okay? It was 15a. 15b. Calculate the ratio of the Broglie wavelength of a proton to that of an alpha particle when both have been accelerated from rest by the same potential difference. Okay, so in the case of proton, so let's use charge of proton as Qp and mass of proton as Mp. What is in the case of alpha particle? Charge of alpha particle, remember that alpha particle contains 2 protons and 2 neutrons. So charge of alpha particle is 2 times charge of proton, because the neutron has no charge, so 2 times Qp. And mass of alpha particle is 4 times mass of proton, because mass of neutron is almost the same as mass of proton. And we have to find the ratio of the Broglie wavelength of proton, so lambda p, to one of alpha particle if both are accelerated by the same potential difference. So we can write this as h over the root of 2 mass of proton charge of proton times v times, or divided by, I'm going to do times h over, so reciprocal, the square root of 2 mass of alpha particle charge of alpha particle times v. You can cross a lot, you can cross h, you can cross the root of 2, you can cross the root of v, and what you have. This is the root of, and up we have mass of alpha, which is 4 mass of proton, a charge of alpha, which is 2 charge of proton, and down we have mass of proton, charge of proton. So we can cross mass of proton, charge of proton, obtaining answer. The square root of 4 times 2 is 8, and this is the answer. The ratio between the Broglie wavelength of proton to the Broglie wavelength of alpha particle accelerated by the same potential difference is the root of 8, because alpha particle has 4 times bigger mass and 2 times bigger charge, and lambda wavelength is inversely proportional to momentum, which is proportional to the square root of mass times charge. Okay, and C. Calculate the Broglie wavelength of an electron accelerated from rest through potential difference of 520 volts. So we can use the equation, this equation directly. This is h over 2 mass charge v. All is given. Planck's constant 6.63 times 10 to the power of minus 34 divided by the square root of 2 times mass of electron is 9.11 times 10 to the power of minus 31, sorry, times charge of electron is 1.6 times 10 to the power of minus 19, and potential difference in the text is given as 520 volts. Okay, calculator, and numerator 6.63 times 10 to the power of minus 34 divided by, and denominator we have the square root of, so here 2 times 9.11 times 10 to the power of minus 31 times 1.6 times 10 to the power of minus 19 times 520 is equal to 5.4 times 10 to the power of minus 11 of meters. Oof. I hope that you've obtained the same results. Yes, A, easy by using two equations, this one and this one. B, the answer is the square root of 8. And C, the answer is 5.4 times 10 to the power of minus 11 meters. Okay, your homework is exercise number 13 and exercise number 14, SOCOS, page number 503. And if you want to see more details about electron, diffraction of electron, there is a device called electron microscope. And how it works and types of electron microscopes are presented in my movies, which were recorded 1 month ago to class 0. So find on my YouTube channel a movie about electron microscope and types of electron microscopes. Yeah, the titles are electron microscope or class 0 electron microscope and second class 0 types of electron microscopes. So please watch also this movie as your homework, if you want, of course. Yeah. Okay, thank you for watching. Any suggestions, comments, write as a post in Google Classroom. Do your homework and see you next week. Good luck, stay at home and learn physics. Bye.